Okay, thank you very much. Today it's my great honor to have this opportunity to share our recent work. The title of my presentation is on the scaling laws for low temperature plasma, macro and micro scales. The title may be twofold, but just I'll give two examples about scaling laws for low temperature plasmas. Sorry. This work was done also with a collaboration with Professor Zhang and Michigan State University. This is the outline of my presentation. First, I will give a brief background of the scaling laws of low temperature plasmas, and also I'll give two examples. One is for microscale, which is an I plasma, and the other one is a microscale, which is high pressure microplasmas. And then is a summary. As we know, we can have plasma scales spans from kilometers to microscale to 1 millimeter or even smaller. So here are some examples. For a kilometer's length, you can have space plasma or mesosphere discharges, which is usually called red spirit discharge above in the mesosphere. So this kind of discharge is very large. Can be of length of kilometers. You can also have 19, and also you can have man-made, human-made atmospheric plasmas, plasma jet, or spark discharges, and also you can fabricate the discharge microplasmas in microscales. But for all these kind of plasmas, they could be low temperature or high temperature. They can be described by the Boltzmann equation. So since the equation for this plasma could be the same, we can then have the characteristic parameters, for example, the characteristic lengths to roughly determine the plasma properties. The very famous one is the Newton's number, which is d over lambda. Lambda is the Levy path of the species, and d is the dimension of the plasma. So by using this parameter, we can simply classify plasma into local region or the non-local region. So for the local region, one can describe the plasma using fluid model with local field or local energy approximations. While in the non-local region, people have to use the kinetic description of the discharge. So we are looking into the plasma similarities in the local region or in the non-local region, respectively. So motivation. So there are previous work about the scaling laws for dynamical plasma phenomena. So here is one paper from Dmitry Roytov from Lawrence Livermore National Laboratory. He had done many pioneers work for the fusion plasma using HME equations, which is also called MHD similarities. But this kind of scaling is more like fluid similarity. So the key problem here I want to emphasize here is it possible to create discharge phenomena, another system which could be smaller or larger than the original one, but the evolution can accurately replicate that of the original one from the initial to the final states. So if this can be done for different devices, it will be very helpful to predict or characterize these plasma properties in unknown devices. So here for the simple gas discharge, we can have of course we can have this kind of geometrically similar gaps, but keeping the characteristic length of these devices the same. For example, we can have PD the same, have the same reduced electric field. Then maybe one can expect a similar discharge in these devices. So this is some example I mentioned before. This one is a red spirit discharge in mesosphere. People have done some simulations for example, they use fluid model with local field approximations to investigate the validity of the similarity laws a low pressure or a high pressure. Can see here for this kind of simulation, a low pressure, even the photoionization is included in the model. The similarity law or similarity properties can still be observed. But at high pressure, we can observe the branching, which is also due to the random distributed photoionization sources. And here we have we also have some previous work. They are arguing that there will exist some similarity properties in the microplasma. For example, in high pressure, when the discharge is generated between gaps of several hundred microscales. So this is all previous work done for the similarity phenomena for the low temperature plasmas. And here, the first example I want to show here is the similarity in IF plasmas, which is a macroscopic similarity. Here I want to introduce. So for low pressure IF plasmas, the electron kinetics is highly non-local because the electron meet path or electron energy relaxation length is much larger than the gap dimension. So previously, by using the experiment, Professor Misobisky, he has done many breakdown experiments and verified the IF breakdown similarity. So in this experiment, he used nitrogen by keeping the F times L the same. That means if you have a high frequency, you have a smaller gap dimension. Then you can have the breakdown voltage overlapping in different systems when the breakdown is versus plot versus PL. So L is a gap dimension. So basically, the similarity in breakdown has been verified for IF discharges, but for the steady state IF plasmas, there could be very different, very complicated mechanisms. For example, here is the electron power absorption profile from peak simulation, and people have observed some plasma series resonance phenomenon. That means the electron can be there could be particle interactions or particle sheath interaction between the slow electron and the beam electron from the sheath gauge. This would induce plasma series resonance, and also there could be beam-like electrons or ballistic electrons that these electrons generated in the sheath, or they can travel across the gap and bounce back between the sheaths without any collisions. So from the EDF, they can have a high energy tail in this profile, in the EDF profile. So all these kind of beam electrons or plasma series resonance is highly nonlinear according to the previous studies. So we are focusing on, can we replicate this nonlinear phenomenon in the similar discharge gaps? So here, by using the peak simulation, we use 1D electrostatic peak simulation to study IF discharge. So the model is like this. The discharge is geometrically symmetric. We control the three parameters simultaneously. For example, pressure, distance, and frequency. This is a scaling factor K equals pressure over the original one, and also by keeping the PD the same and also F over P the same, we can tune the PD and F in the case gap from the base case. So now we did the simulation from the initial to the steady state, and keeping with the same FD, PD, or F over P. Here, it just shows the example when the scaling factor is 10, you can have the same spatial temporal evolution of the ionization coefficient, ionization rate, and also the electron current flux. So you can see here the profile of the from original one and the scaled one with scaling factor of 10 are exactly the same from the peak simulation, but the magnitude are in proportional, which is proportional to the k square. Here I also did simulation by slowly increasing the scaling factor k, so you can see the peak simulation results agree well with the theoretical prediction. That means this similarity scaling are rigorously maintained and can be demonstrated by the peak simulation. So, and also, as I mentioned before, there could be spatial temporal or plasma series resonance phenomenon during the sheath expansion or sheath collapse. So here, I also present the spatial temporal scaling of the electron power absorption, which is based on the ZRE. So these three figures shows the ZRE profile with different scaling factors. So k equals 1 is the base case, and k equals 5 and 10 is the scaled down cases. By scaling down the gaps, we also increase the pressure and frequency to keep the PD and F over P constant. So here you can clearly observe that although the magnitude of the ZRE value could be enlarged, but the profile is exactly the same. And also, if you scale the ZRE profile using a periodic average value, and you can see the spatial distribution of the time average, the ZRE profile are overlapping. That means this nonlinear plasma series resonance can be replicated in different systems as long as you keep the PD and F over P the same. Here I would like to briefly introduce why this can be this phenomenon can be replicated. So since in the simulation I keep PD the same PD is a well-known similarity factors, which is representing the collision numbers between the electron travel across the gap. And collision F over P is the collision time. So because the collision frequency is proportional to the pressure, and if you rewrite this parameter, you can obtain that F over P is represents the inverse of the collision times of electron during one life cycle. So here, that means for the this is the electron energy probability functions from the peak simulation. So figure A is the base case. By decreasing the gap distance, you can have higher energy tails of electrons, because in this case the gap length is smaller. The more electrons have become ballistic, so the higher energy tails increases. And also the high pressure from D to C have a high pressure, and you can see because pressure is higher, the high energy tails is more truncated. So, but the interesting part is as long as you have the same PD value and F over P value in figure A and figure D, you can have the same normalized EPF. Here the EPF is normalized to the electron density, so this is normalized. So the profile of the normalized EPF with a scaling factor of 10 is exactly observed. But here we should note that we don't consider standing wave effect. So this paper is a very early paper about the similarity theory, but this paper is still with local field approximation. So here our results confirm that the electrokinetic invariance can be obtained without these assumptions. So also we have some scaling of the beamline electrons. So in the peak simulation, when you consider secondary electron emission from the surface, this secondary electron emission, when they cross the sheath, they can be accelerated to high energies, and they can be captured in the EPF with these wavy tails. So, but here our results, if you keep the PD and FOP the same in the scaled gap, you can have the same scaling behaviors of the beamline electrons. For example, you can see from figure A and figure D. Here I further look into the compare the similarity law and the frequency scaling law. In the similarity law, people have to tune the pressure, distance, frequency simultaneously with the same scaling factor. So that means that the devices are not in the same size. Here, for the frequency scaling, you can just tune in the frequency and you can observe the parameter, how the parameter behavior versus the frequency. So this is called the similarity scaling and frequency scaling, respectively. But note here, for the frequency scaling, the dimension is not scaled. Also, dimension and pressure are not scaled. Here, we first confirm the validity of the similarity scaling with and without secondary electron emission. You can see with secondary electron emission, the electron density is slightly higher, because in this kind of discharge, the IF plasma is operating in the alpha mode region, and secondary electron emission is not that important. But when I compare to the scaling from the frequency scaling and to the similarity scaling, you can see that in a certain region, in most of the region, they will have the same, approximately the same scaling, but in some of the regions, there is a deviation occurs. Because for this kind of discharge, when the frequency is lower, certain cases, the quasi-neutral, the stationary bulk plasma region is not does not exist. So you can see here for the left branch, left-hand side is rigorously maintained similarity scaling, and right hand is the transition to the deviation of the frequency scale. This is because for this kind of, especially for figure F, you can see there is zigzag kind of quasi-neutral region. This is the electron density profile. This is the GDP profile. You can see also for this one, you can see the same electron absorption profile. For here, we can have a very different kind of heating maximum, because in this kind of heating maximum, the bond heating becomes important, and I'll show you later. So here, this one is the time average GDP profile for the similarity scaling, the overlapping ideally. But for this one is a frequency scaling. For the blue curve and red curve, they still follow the frequency scaling, traditional frequency scaling, but for the red curve, but for the green curve, this kind of electron power absorption is becoming ohmic heating dominated. That's the reason for the violation of the frequency scaling, because the fundamental electron heating maximum is changed. We also compare to the conventional analytical expression from Lieberman using the global model, which they are also consistent. And here we show the electron kinetic invariance for the similarity scaling and for the frequency scaling. And for frequency scaling, we also have the electron kinetic invariance. But when the frequency scaling is broken, we can observe the EPF profile no longer overlapping. Instead, it will have a boosted highlighted tail. And the other example I want to briefly show here is the microplasma. So this kind of discharge can be fabricated using MEMS or lens technologies, and we can have even 3D microplasma arrays. previously there is a paper published in Nature. They're arguing that we can scaling down the microplasma devices, can be utilized for the analytical chemistry. So, but these haven't been verified or demonstrated before. So, but in our study, we are more interested in the electrode surface morphology. For example, you have a single or multiple surface protrusions. Of course, you can have a local field enhancement or the shielding effect between protrusions. This kind of surface morphology will have significant impact on the breakdown, also for stable plasmas. And previously, they have some discharge investigation on, for example, breakdown with complex surface. So people, for example, for this one, they have stage electrode or the whole cathode electrode. At different pressures, in this kind of gap, they have the gap distance is no longer constant. They have a maximum value or minimum value. So at different pressures, for example, the right branch, the Parsons curve, the breakdown will choose the shortest gap distance, and the breakdown occurs close to the edge between the anode and cathode. While low pressure, which is left branch of the Parsons curve, the breakdown occurs inside the whole cathode because the breakdown chooses a longer path. So there are also some simulation about the plasma propagation course, bilateral course, which is can be used, could be instructive for the plasma medicine indications. And here, our study focused on the breakdown with multiple surface protrusion on cathode. So here we investigate the shape of the surface protrusion, which is a ellipsoidal protrusion with parameter A and B, and also we have the spacing between the protrusions, which is X. So A and B, the aspect ratio of A and B can adjust the field enhancement or determine when the breakdown chooses the shortest gap distance, which is the minimum, or the breakdown can occur from the longest gap distance, the max. X also can tune the shielding effect. So here our main results, confirm that with a larger protrusion spacing, the Parsons curve can be flattened. So, but when the X equals 2B, that means this protrusion is too close, then you will have the field enhancement is not that, the impact of the aspect ratio is not that significant because they're too close, and which is makes the surface is more like a flat surface. So here we also compare the results with the cathode with surface protrusions, and also compared to the flat electrode. You can see when X equals 2B, the breakdown curve are almost overlapping to the flat electrode. So more interesting, we have also looked into the perturbation of the potentials of the cathode protrusions, and also the field enhancement. Have a large spacing, we have a larger field enhancement on the protrusion tip, and also by tuning the aspect ratio of the protrusion can have different field enhancement. Yeah, but most importantly, we look into the geometrically similar microgaps with concentric cathode protrusion, and X and K is a scaling factor. But here we only consider the scale, the dimension with a factor of 2. Here, A1 and A2 are the similarity gaps, similar gaps, geometrically similar gaps. But here we have four Parsons curve, which is breakdown voltage versus pressure. But when you scale the pressure with the factor K, which can be considered as more generalized Paschen's curve, Paschen's law, then you can have the breakdown curves are overlapping in geometrically similar gaps. So the Paschen's curve in A1, A2, or in B1, B2, they are overlapping ideally. So here is the conclusion. We have shown the similarity properties of low pressure plasmas in non-local kinetic region and demonstrate the electrokinetic environments. We also found that the similarity, compare the similarity law and frequency scaling in the different frequency regions, and found they have almost the same scaling relation for electron density, but the frequency scaling is not rigorously maintained. It might not be rigorous, it's just an approximate relation, but can be violated when the sheath becomes much larger. And also for the microscale low temperature plasma scaling, we have confirmed that the breakdown scaling for example, for the Paschen's curve with when the cancer protrusions exists. And we look into the effect of field enhancement, electric field distribution, electric shielding. And also, we found that the characteristic lengths that determine the operational microplasma, the steady state. Here is acknowledgement. We are grateful to Professor Hanjun Li for his comments and discussions, and appreciate the support from Air Force or Office of Scientific Research. Thank you very much for your attention.